think I'm recording. And I hope there's audio. There should be audio. I'm not 100% though. All right, I'll let you do that and then. Hello? We're good. Just gonna start and I guess you can do this with me. Why?
It like doesn't pick it up unless you're like,
All right, well, let me try to change the audio.
yes, good.
Sounds good?
Tree.
Well, let's just do it. So let me open up my slides and then we can just go. Um, oh, bro, that's one. And let me open up the other slide deck. Okay. So let's kind of just go. All right. So this is the recording for the FPG Gators VHDL Basics Workshop Part 4. I'm Yoni. I'm also joined by Antonio. Um, Great turnout. Um, but we're gonna keep going. So let's just start. So I'm gonna do a little recap of George had the VHDL Basics Part 3. He had a workshop. So I'm just gonna kind of just really quickly cover his slide deck, and then we'll get into the content of this workshop. So these part 3 and 4 kind of go together, but they cover sequential logic. So just recap, what is sequential logic? Last time we talked about combination of sequential logic with processes. Sequential logic executes statements in the order that they're written. Sequential logic circuits have memory that stores information using flip-flops between clock cycles. For those who are familiar with digital logic, digital design, you think of flip-flops and registers. Those are the foundational components of that synthesize sequential logic. So yeah, fundamentals of sequential logic. Flip-flops are the core component of sequential logic because they enable the circuit to store information between clock cycles. There's these different types of flip-flops. D flip-flop, which I think most people are familiar with. That is, the data going into the flip-flop is stored and becomes the output of the flip-flop on a clock edge, triggers on the clock edge. There's also J, K, and T. I'm not going to get too much into those, but they exist. We'll continue. So how could flip-flops be so important? Using multiple flip-flops, you can create registers with different bit widths. Registers are used in every sequential logic circuit. So here's a little snippet that we'll get into later. Dr. Stitt's guidelines, of course, very important. If there's something to take out of these workshops, you can always learn so much from Dr. Stitt's tutorials online. For those that probably have heard of him already. But just to cover these two guidelines, sensitivity list should only have clock and reset. If there's an asynchronous reset, basically, and into part 2 of this, if reset handle reset, else if rising clock edge, that covers the functionality within a process to synthesize to proper sequential logic. So let's just continue. So yeah, George covers FSMs, finite state machine, a circuit that transitions between states based on inputs and clock. There are two types. More outputs depend on the state. Mealy outputs depend on the state and the input. So to create an FSM, we must design the stage, draw a diagram with transition logic, and implement the diagram. All right, so here's a link to some of that stuff. This is just covering more of that. Here's some examples that we'll cover later. How can we build on registers and FSMs? Registers are used in every sequential logic circuit storing data on clock cycles. So here's just an example of, I'm not entirely sure which, it's like a CPU, yeah, but I don't want to say anything not super factual, but we'll just continue. So basically, yeah, using many registers allows for the creation of data paths, functional unit that transfers information between registers, performs logical operations. Michael, welcome. Yes. So FSMD, finite state machine with a data path. The logic of the state machine and the data path is all encompassed within the same architecture. Data path executes logical operations. FSM controls the sequencing. So an ALU, UART transmitter filters. These are just some examples, and these are all you're able to implement all of these within on an FPGA. And George linked this example from Dr. Stitt's tutorial, of course. So here we go. Live coding, that is the purpose of this workshop. So let's kind of just, what everyone's here for. Get into the it is. Oh, it's not. Thank you. Technical difficulties. Thank you. Thank you for noticing that. Weird. All right. So this workshop, VHDL code, simulations, let's get it. Yeah, so I'm just gonna kind of just go through some code that I have prepared and we'll code together. So yeah, let's just get into this. So we're gonna first build from flip-flops and registers into more complex circuits. But actually, something I forgot. Antonio, hold on. All right. So making sure. So we're basically gonna. Oh, see, no, so I don't want that. Have it disabled, but it's still doing stuff. I don't like that. Why is it doing this? It's not what I want. Hmm. Something for the diff. Sorry, guys. For the love of the game. All right. No, dude, just uninstalled you. Dude, that's craziness. I don't like this. I'm sorry, guys. I thought I had this figured out. Where do I turn that off? I thought I figured this out. Um, Let me do that. Uh, all right, we're back. Sorry about that. We figured it out. Right. So basically, without getting too much into the nitty-gritty syntax of VHDL, we're basically gonna just actually first, sorry, let's go over a flip-flop. So as we described previously in the slides, a flip-flop compared to a register is just a 1-bit register. And essentially a flip-flop stores either a 0 or a 1 on a clock edge. For the purposes of this workshop, I'm just going to make a we can talk about a synchronous and asynchronous resetting flip-flop and register, but we're just going to make an active high flip-flop. So first things first, with all of our sequential circuits, we need our clock signal, which is an input standard logic, right? Making sure I got this right. All right. And then what is the next thing we need? So we also, right, we have our reset. It's also necessary to encompass the functionality of the flip-flop, right? So we have a clock, we have our reset signal, right? So without getting, without drawing out what's going on, right? A flip-flop is essentially like a little box. You have a clock signal, a data line, and then the output. And basically on the clock, it will update the output to whatever the input is on that clock. So besides that, we just need our input. So we'll just call it data in, D in. That's going to be an input standard logic, and then D out.
Yeah.
Right. And then this is the proper syntax for the port of our flip-flop. Thank you. And we can also write it like that. Right. So this is our port, right? Clock reset, data in, data out. So next thing we need is architecture. We'll just call it FF of our flip-flop, right? And then we can end the texture like that. It's throwing a syntax error, but just so we can avoid these problems, I'm going to add these files into the into this project that I have. So let's just add them. Just add it. Let's see if it's still upset. Okay, so am I missing something? I don't know what the error is. Okay. Or maybe it's missing the begin. That might be why. Oh, that's exactly why. Okay. Yeah, for some reason at this point, if you don't have the begin, it kind of just throws errors. But basically, within this little block here from the begin to the end is where we can have our process block, which basically allows us to encapsulate the functionality of a flip-flop that will synthesize correctly. So this entity flip-flop, the behavior that we write for it will synthesize properly to what we want whenever we're programming FPGA, and that's at the end of the day exactly what we want. So we have a process here. And then as we were saying before in the guidelines, right, you need for an asynchronous reset, you have reset in the sensitivity list. And then if we want it to be synchronous to the clock signal, we take this out. And essentially, like George was describing from the past workshop, basically the basic template structure you want for a sequential process block is basically going to do if reset else if rising clock edge, essentially. That's like the structure that you want. So we'll do that. If reset is equal to 1, then, and then else if rising edge of the clock, then, and so this is the structure that you want to have for your sequential processes. But essentially, right, we have dn, which is a bit, dout, which is a bit. This is how we define we need to define our output dout, right? So if reset is true, active high reset, right? Right. If the reset is true, what do we want to do? We want to reset. And for the case of this register, we're just going to set it to 0, right? But whatever reset value you want to define your reset logic. And then essentially, right, on an edge, what do we want to happen to the output, right? Right, we want it to be data in. And this is the basic structure for a flip-flop, right? 1-bit flip-flop. I hope the speed is okay. I know we were talking about trying to get this at the right speed, so I hope it's not too slow. Hope it's not too fast. We're still working out, but obviously for the context of workshops, we're kind of trying to expect everyone might have a lot of different levels, so we're just bear with it. But anyway, this is the architecture for a flip-flop. And if we go back to our Questa project, we can just do that. We can see compiled, no errors. So I kind of want to immediately go into a register because register is so simple for the flip-flop, and I did not make a flip-flop test bench, but I have a register test bench. But we'll just get right into register. So the difference between a register and flip-flop, a register is like a flip-flop but can have like n many bits. So basically the exact same port as a flip-flop, right? So we can have it like this. We can have the exact same port, but data in and data out, right? What will they be now? We can have it standard logic vector, right? So it's a vector of bits. And depending on if you want to have a generic width or something like that, you can define that. But for the context of this workshop, I'm just going to explicitly define that. Let's say we want to have a 4-bit, right? 4-bit register. It will be 3 down to 0. Same thing, standard logic vector. And same thing, 3 down to 0. Oh, wow, I didn't do that. Okay. And yeah, this is essentially the exact syntax that you want to have. Clock, reset, data in, data out. But now we have a very different width for the bus. So this creates a bus for a data line. And yeah, basically this is the exact, yeah. That's what I was saying. So you can create what is it, a generic. So I think generic, and that'll be what is it? Width. Okay. So this is the data type for creating a generic. And then essentially what we can do here is we can define our width. Let's say we want it to be 4 bits, right? It will be 4 bits. You would want to create it with -1 down to 0 since we're indexing at 0. So that'll be 3 down to 0 to be 4 bits, right? And we can have this, and this will also, whenever you're having, whenever you're going to be like structurally connecting entities and things like that, having generics can make it easier, so you don't have to go into the exact entity and have to manipulate explicit declarations of the sizing and all that. So not to get too much into that, let's just continue. So architecture, we'll just call it register. Okay, it doesn't like that. It's a keyword. I don't know. Of here we go. Right. So this is again begin. Right. This is the outline of this is template outline of an architecture. And then same deal. Process, clock, reset, this being asynchronous reset. But we will get into that with the test bench I made for this. So same, very similar deal to the structure of the flip-flop. Very similar in the context of a register. It's just a variable amount of bits for the data. It's gonna be the same deal. So if reset is true, then else if rising edge of our clock signal, right? And you can also change this depending on the behavior. If you want it like falling edge, there's a lot of things you can do in the syntax, but for how we understand the behavior of our test bench and the behavior of whatever context you want this entity to behave in, you can define that in the behavior here. So same deal. So now, right, we can't, for instance, let's just say D out, right? This doesn't work. I mean, it's already throwing me an error because character literal does not match subtype vector. And if I add this to the project, will this go back to me? Okay. Here we go. So if we try to compile this, right, one error, right, same. This will basically, if you're not programming with a linter or whatever extension, right, you can use the Quest the simulator to tell you your error. But basically, right, I'm explicitly defining the output to be this bit 0, and we don't want that. And if we like explicitly said 3 down to 1, right? Let's say we wanted to do this, right? We could have it like this. We can explicitly be like 1, 2, 3, 4, like that, and we can compile that, and that works, right? But let's say we want to have a variable width, right? How do you define number of zeros, right? How do you do that? So there's this thing in VHDL that allows you in system verilog, you can do like this little apostrophe here. But basically in VHDL, you do something like that. And as you can see, this is the latest. Let me save that just to make sure, right? This is the way that you declare it to be the entire bus to be 0. And then besides that, you just do what we did before, where you define D out, D in. And these typings match up. All right, fantastic. So let's get into simulating this really quick. We're gonna have another workshop in the future talking about simulation and test benching and all of that. But for the purposes of this this workshop, I know why. It's because I have them name different things in the test bench. So obviously, like how a lot of other entities work, is you need to ensure that that your entity that you're referring to is the correct name of your entity in basically your work directory. And okay, so let's just go one by one. So the first thing here, clock and reset are both named the same thing. But this needs to be called basically, what did we call it? We called it D in and D out. So this needs to be called D in, and this needs to be called D out. And then if we go back, right, this test bench works. So left side is your entity, and right side are the signals that we have defined driving our dot. Same deal, D in, D. Okay. So now both of them should compile. Okay. So first I'm going to run Dr. Stitt's test bench. Hopefully this runs pretty smoothly. If it doesn't, I might honestly go to mine just because I am not trying to just debug this in this workshop. But yeah, all right, so this worked. Obviously, register variable width. Yeah, Dr. Stitz also does a variable width, so I'm glad I thank you, Michael, for mentioning that. Basically, yeah, test completed. I wrote a test bench that we can look at a specific example, and we can talk about the reset more. So what I'm going to do is I'm going to start the simulation on this is my test bench. Yes, I can upload the code to the repo somewhere. But basically, okay, so we're gonna zoom in a little bit. And hopefully this makes, I didn't write a lot to test. I just wanted to show some functionality of the register, yeah, of the resetting logic. So basically, you can see here that we start with our reset high, and basically on this clock edge here, we can see the reset is low and clock is 1. So on this edge, it will update to whatever input is. So since it's still 0 here, it won't update. But then on this next edge, we can see like over here, this is a great way to like see exactly what's happening on that timestamp. The clock is 1, right? This is the transition edge right here. As you see, kind of like locks in right there. The reset is 0 and data is that. And then basically on the next edge, it updates here, and you can see that basically that's basically the functionality of a flip-flop. So on the clock edge, it updates, and basically you can see at like 1 cycle latency delay, which is the functionality of a register. And then yeah, so basically I wrote a little thing here to show that reset, on this clock edge, right now our register is asynchronous. So as you can see, this is past the clock edge and it resets right here. You see how it goes from 2 and then it goes right back to 0. So even though this isn't synchronizing with this clock signal, this the behavior matches, it updates the signal on that reset asynchronously. So let's just say I take reset out of the sensitivity list and I recompile this. We'll basically see that this doesn't happen until 2 won't be cleared until over here, the next rising edge. So let's, right. So, right, also, because we need resets asynchronous in our old circuit. Now, since it's synchronous, we're waiting till the edge for it to update. But basically, the logic that we had before happens, and basically we can see that what's happening here is it's not, it's clearing. Am I bugging here? Shouldn't it clear here? Antonio, do you see something that I'm missing? I took it out of the sensitivity list. You're saying in here? Oh, I have to do it there. Oh, right, because on the falling edge, it right, that makes sense. I see. I should work like that.
Wait, no,
Yeah, but I'm saying, well, what you're saying makes sense because it's even though the because this basically triggers the process whenever the
clock changes, yeah, but the sensitivity list, but if you want to make it synchronous, reset has to be here,
where?
inside the rising edge clock, right?
Oh, you're so right. I meant
It's
to
process clock and reset.
right, but you're saying
Yeah, that's always.
what is it you do?
You only have one reset. Yep. But inside the rising edge.
So you do it like this.
Yeah.
Yeah. Thanks.
Yep. Okay, the next one of that. Yep. Because then it'll only trigger. It'll only trigger at when.
Okay. So it stays until, the so basically the process will trigger basically whenever any of these signals of the sensitivity list change. So essentially, even when the reset changes, it'll still trigger this process, but it won't actually execute this line because of this nested functionality of the rising edge. So basically, we're waiting for when it's a transition from 0 to 1 of this clock signal, which is how we're synchronizing our circuit, how we're expecting to synchronize this register. And basically, on this next edge is when it clears. So yeah, that's the functionality of a register. I know that took a little bit of time, and I'm apologize again if that was slow. But yeah, we're gonna keep going. So let's get moving to the next um to the next topic. So next topic is a counter. Um essentially, right, what does a counter do? We essentially want to, depending on the bits in the counter, um increment an output and basically store that output um, and internally and display that and increment it each time the clock happens. So let's just kind of get going, start writing some behavioral code for this. And what I'm going to do here is I'm going to make a counter HD. Right. So second. There.
Thing.
library. You need to also include this library IEEE standard each time. You need to use IEEE dot what is it? STD. Yeah, this guy all right each time. And then here we go. So we're gonna make our entity counter. And then basically end counter. So counters are useful for a couple things on FPGAs and synthesis. So like if you're trying to do like a clock divider, for instance, or a clock generator, you would use like a counter. And that can be implemented physically to basically slow down or manipulate a clock if you're doing some sort of like CDC or something like that. Even if you're just trying to generate that signal, that's just an application of of a counter. So same deal as before. Port. This is your port declaration. So what do we need, right? Because we're doing a sequential circuit, right? In CD logic. So we need a clock, reset, and then we'll have a control signal. I'm taking this counter example from Dr. Stitt's tutorial. So he has a like a enable kind of thing. Up. Basically, if up is true, you define all of this in the behavior of this counter. But if up is true, essentially we want to count up in the counter. And if it's false, we'll count down. So, and we'll treat it as active high. So it'll be up is true is 1 and down and false is 0. So in and then STD logic. And then we'll have an output out STD logic. And then for the case of my test bench that I made, it's going to be a 4-bit, but we can do what we did similarly in the other example where you can have a generic counter, or it can be a generic width to be like a C log of C log is like the library that you can use, like a math library, but like the log of the number of bits. This the log of the number of bits minus 1. So if it's like if we want to have like or like the max value rather. So if you want to have like 16, that would be like if we want to count from 0 to 16, that would be like log of 16, which is 4 minus 1 is 3. So it'd be 3 down to 0. So like this counter can count to 16, for instance. But that's essentially how you would, if you had a width, you would do like the C log of whatever, like the number of like the max like value in the counter you would want. So if like 16 was the max value, you would do that, or 15 or whatever. So, but for the context of this example, not to get too much into that, we're just going to explicitly define it. So architecture count of right. Okay. So this is the basic template of our counter. And then essentially, like I was saying before, we're going to just kind of follow the same guidelines before we kind of get into any actual behavior. So if active high reset, okay. So this is like the bare bones template for like how you want to like start any sequential circuit, right? So let's define the behavior of what we want this counter to do. So basically, we'll just say we want the counter to start at like 0 when reset's true. And then basically, depending on if up is true, we want to start incrementing it. And then if it's false, right, else, then we want to like decrement it. And another thing we can do is we can start implementing the use of signals in our circuit. So a signal, we'll just call it like our count R. So this convention underscore R, basically, so a convention of like describing to like the user that like whenever you're reading this, that this is like a register, for instance. And what all I mean by that is this signal, right? In VHDL, you basically assign like a signal, like count underscore R caret equals blank. And then basically this signal in this process will synthesize to like the behavior of a register that we had in like our previous example where we're doing D out caret equals D in. This caret equals of this D out port signal. Basically, this internal signal count R will do something really similar where it will essentially synthesize to behaving like a register because it's in this sequential process block, if that makes sense. So we'll see that in our simulation, how this count R signal will have the behavior of a register and behave how I'm expecting it to, like a register throughout the circuit. So let's just kind of continue. Let's finish this declaration. So it'll be a standard logic vector. And all we can do is just define it to be the same as our output. And basically we'll just manipulate this this count R signal. And then on the outside, what we can do is we can do chill. Oh, okay. And then we'll do is count R, right? So this is basically like outside of the process. This will basically assign this combinationally. So it's kind of like a wire here. So let's kind of just continue. So when it's 1, like I described earlier, we want to like essentially reset the count of the counter, and you can decide what you want to reset it to. But we can do other 0 here, but because I hard coded the width, I'm just going to make it all zeros. And this is just saying like we'll just imagine the vector in binary representation, and this will just be like unsigned integer like 0. So essentially, let's get into the actual behavior on a clock. So like I was saying before, we have this up signal. So we'll have this nested if up is true, then, and then else, right? So up is true, else is whenever up is not true, so false. And yeah, so basically when it's true, what do we want to do? We want to increment our count R. So, I'm starting to realize, so I think VHDL has more of we need to be more explicit with our typing. So we'll actually make count R in integer. And then we can actually just say that it's 0 here. And then basically here we will, and just to ensure we're doing this correctly, let me add this file to the project. And you can do this as you're programming any entity. You can really just add it to a project. and just compile it along the way just to make sure that you're not. Okay, so I have an issue here. Oh, I know where the issue is. The issue is down here. Count R. So we need to cast this std logic vector. And then I need to do, I think you have to do 2 unsigned because you have to cast it to unsigned and then I think 4. That's right. Oh, and I need to include the library, the numeric standard. So yeah, whenever you're doing some casting, you need to use some other numeric std. Oh, okay. Yeah, so you need to include some other library things that make it easier to program these casting things in VHDL. That's just something that exists. You just need to be aware of it. But essentially, the output here, standard logic vector, it needs the typing at on the outside of all these like parentheses and stuff need to be the same typing as whatever you're assigning to. So it needs to be standard logic vector. And then you can't do standard logic vector or integer to standard logic vector. You need to do 2 unsigned because you can then cast an unsigned vector to a standard logic. That's just a weird explicit thing that you need to do in VHDL. I didn't make the rules. I'm sorry. I didn't do it. I've been really serious so far. This is too much. I've been so serious. I've just been on teaching mode. Okay. By the way, so far so good. It's good.
Yeah.
Okay. No, I don't really know if I'm just yapping or not. Okay.
Good.
Thank you. Okay, bet. All right. We'll keep going. So, yeah, let's just continue programming this. So, right, if up is true, what was that? So, up is true. So we want to count up, duh, and then, right, we want to count down. So in here, we want to count up, and then we took care of creating this register. So here, if up is true, we essentially want to do this count R increment count R plus 1, right? That makes sense. That's good. And then here, let's do the same thing. Count R equals count R minus 1, so decrement, right? So this is pretty good behavior. And that's pretty much exactly what we want to do. But there's something that we'll notice that honestly, I might simulate this first. Before I actually fix, obviously, I know what the problem is. But, you know, from looking at it, you're like, okay, that makes sense. You're just incrementing and decrementing depending on like that flag to up or down. What's the problem? And we'll get into that in 1 second. Let me close this, open up this test bench. So I have this, so now we'll just call it counter because that's the name. This is the name of the entity from back here from the file. Let's compile all. They compile. So simulate, run simulation. This is my test bench. It's obviously not very thorough, but we're still good. Still good. Still good. Still good. So let's pull these signals into here. And if we run that, there's some truncating error or warning just because it's trying to do something. But anyway, let's yeah. So basically, right? I don't know. Let's see what's happening here. So it's wrapping around, which is what I want it to do, but I'm not sure if what um my fix was going to be is going to fix this warning. But Two unsigned vector truncated. Okay, I'm not really exactly sure why it's doing this exact warning, but the thing I wanted to note was um Dr. Stitt included a check of the count to basically ensure that whenever the count hit its overflow, so basically since the counter is through 4 bits, right? 2 to the 4 is 16 minus 1. So it'd be the values would range from 0 to 15. Whenever the count hit its max value, he explicitly like reset the count to like going back to 0, so it would wrap back around. It's doing it here, but I think in synthesis, you would need to explicitly say that. So basically, and I just think depending on like having, obviously in simulation, there are some things that behave a certain way, and I'm not entirely sure, how big of an effect this might have, but let's just, for the safety of our circuit, you basically want to have like another check and basically be like, if our count equals like that max value, since we're incrementing, then and then else, right? So I want to increment regardless, but if we get what, right? But if we get to that max value, what do I want to do? I just want to set our count R to 0, right? So we hit our max value, the next value will then be 0. And then similarly, if count R equals 0, right, it hits the minimum value from decrementing, then else and if, right? Similarly, we'll do the same thing in this else statement. You'll put that there. And then if it equals 0, we want to set count R equal to 15. And that's just explicitly setting the value when it overflows. And I think this is important in synthesis, but in simulation, we're not really seeing a very problem, but we'll reset this. I don't think it'll fix this warning we're getting. Oh, and it did. So maybe that's what it was. So yeah, if we go one moment, if we get all the way back to our test here, we can see here we go. We're going and we're overflowing here at 15 to 0. And then we keep counting up, up, up. And then basically whenever what am I looking for? Which guy? This guy. All right, we're counting up 15. We get back to 0, loop back around 1, 2, 3, 4, 5. We go, so right, up goes false. So then the next value in the next edge is 4, 3, 2, 1, 0, wraps back around to 15, and it fixes that issue. And basically that is the functionality of a counter. And basically, let's just say we want to do like a clock divider or something. Basically, we'll have a value without just counting, right? Obviously, this is checking a max value or checking whenever it hits its max value. But essentially, we can also have a nested check in here or something. It'd be like if count equals like a target value, you want to do something to some signal or something. So that's just an application of a counter. And then you can actually probably in just a counter, you just want to count up that's doing some division. You won't even need like an up down signal. You could just do like this check. If it equals 15, reset, else you're incrementing. And then basically in here, yeah, you could just be like, if it equals the value that we want, you don't even need to check a max value because maybe it might not ever get there or something. You could just be like, if it equals our target, we reset it. But if not, we want to increment it. and this can maybe be like a target value or something like that. So anyway, yeah, that is the counterexample. And I think my test bench was showed just the bare functionality of that. Dr. Stitt's test benches, I think test a little bit more robustly than what I'm going through, but we will cover proper methodologies to simulation in future workshops. For the scope of this workshop, don't worry, we still good. Let's keep going. So, um, I'm obviously piggybacking off of George's slides, but I want to do programming coding of this more state machine, right? So as mentioned in George's slides, um, yeah. So more outputs depend on the state, and immediately outputs depend on the state and the inputs. But and as we can see from here, basically this done signal and acknowledge or whatever is happening on the transition. And basically, um, in this more state machine, output is defined by the state. So we'll see the implications of that in simulation, but let's just kind of get into this. This is kind of a diagram I'm looking at. I'm going to be like, all right, we have the port defined here. We have kind of the flow of the state machine. Now you can apply this to an algorithm. Dr. Stitt's tutorial covers like bit diff. So it's an algorithm to calculate the difference of bits of like two vectors, I believe. But in DD, you go over like a GCD calculator. So basically you have two like vectors like A and B, and then basically whenever you start the state machine, by the time it gets to the end of it, there'll be like some done signal that'll go true when it's done calculating everything. And then the value of the output should be like valid, and that is like the calculation of the GCD of those two vectors. So that's like an application of this, but getting good at taking like some pseudocode or taking like a diagram like this and being able to implement that in some code is a skill that, like everything else, and you just need to kind of practice it. But being able to break down a algorithm into like states, something like that, was something that George was getting into with like FSMD and stuff like that, where then you can have a data path and a controller to control some process and things like that. So let's just kind of get into it enough. Yeah. All right. All right. So same deal. Library, IEEE, use IEEE, STD. Okay. And then I'll do the use IEEE dot numeric just in case. I'm not sure if we need it yet. Okay. Entity FSMD. Thank you, bro. Um, so FSMD is a combination of your FSM, your controller, and your data path. You assigning the data and values, all in the same architecture. But if we're gonna go back to this guy, right? We can look at this here. So 3 inputs, clock, reset, enable, and then 1 output. So that's our port. Pretty easy to find here. So clock, in, STD, logic, reset, in, STD, logic, enable, in, STD, logic, last output, out. And this is going to be a vector. As we can see, it is 4 bits. SD log, no, that's not what I want. Logic vector of 3 down 0. Okay. So that is our port. Still good. Let's continue. Architecture. You can name it whatever you want. What was that, Antonio?
Nothing.
Okay. Heard that. I hope everyone's having a great day. Yeah, man. X. I'm having a great time. I've never seen this in my life before, so this is craziness. Great. Now, I've never seen any of this code in my life. I just can't do
I
it.
just do.
Oh, and the issue is that I just need to call it FSMD. That's why that's there. Okay. Okay. Cool. Cool. So, yeah, let's just continue. So, oh wait, where did it go? Where did it go? It's right there.
And what?
Okay. So we have, so now we have, actually, let's continue with what we were doing before, our sequential guidelines. So if reset equals 1, then else if rising edge clock, then and if, right? Why are you mad? Why are you mad? Why are you mad? I'm missing something somewhere. I know why. Because I forgot my guidelines. Yeah, don't do that. Don't be dumb. Leave that to the professionals. Me and Antonio and Michael. Sorry, guys. All right. Now it's good. I'm like, man. So it's been a long day. All right. This is our outline. We're still good. So let's define the output here. So, right, initial state 0. Oh, so right, we're defining each of these little bubbles as like a state. So you can do, I'm just gonna like cheat really quick and see the exact syntax. Relax, guys. Take a rest. So, yeah, so we can see here, there's this thing you can do with VHDL where you can create your own type. Well, I'm done. I'm done. I had enough. Nah, Michael's right. He's right. You guys, he's probably right the whole time. How do I doubt? Anyway, so we have this type state T. So as you can see, we like create a signal state R. So this is the register that holds the current state. And we just define this as like an enum kind of deal. So basically each of these state 0, state 1, state 2, state 3, like we have in this image, state 0 through state 3, we can then like assign state R to like these values. So like here we could be like state R equals state what? State 0, like that. And that like is allowed. As you can see, yeah. So we're like allowed to assign these possible values of state T type to state R. So that makes it easier because as you can see when we get into simulation, I'll pull in some signals and we can see that state R will like have the value state 0, and it makes it easier whenever you're trying to see what's kind of going on in simulation. You can make it easier on yourself, and that's at the end of the day in an industry position like internship or a job or whatever you're doing, research, making it easier on yourself in simulation is the best thing. So it's just something for us. And yeah, let's just continue. So basically, whenever we want to, whenever we want to create a FSMD, we want to basically create like the best way of doing this is to have like a case statement. So we can do like case state R. I don't want to mess up the syntax of this. So is, okay. So we do like that. And then you can do end case. So that's the syntax. And then you can be like when it's state, or like when state 0, you go like that. So this is like the syntax of basically defining what's happening at each state. So state 0. So we can go like state 0, state 1, state 2, state 3. And this is basically a great way of creating a structure each time you have some sort of image or some pseudocode. Whenever you can break it up into states and things like that, before you actually start programming the behavior, you can just kind of break it up into a skeleton. It makes it easier for your brain without overloading just kind of all the behavior, what's going on. So yeah, so at reset, we want to be at state 0. What's happening in state 0, we define state R to be right. If we go back here, not state R, sorry, output. My goodness. Output. Oh, I am wrong again. My goodness. So that's what we want in state 0. We want it to be, that is our output. And we'll see, since this is a more state machine, we'll see something different from when I will alter this to be like a mealy state machine. But basically, since the output is dependent on the state, it'll update a cycle late from the actual state. So let's just define kind of what's going on in each state. I did this before, but looking back, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, blah, blah. What'd you say? I bet. Okay, just making sure. So then, yeah, so that's kind of what's going on in each state. And then basically we can see whenever enable 0, it stays within the state. And when it's true, it transitions. So if enable is 1, oh. So basically we want to do this each time. And then we can do state R, right? What is the state after this? It goes from state 0, state 1, state 2, state 3, and then back to state 1, as you can see in this diagram. So what I want to do is equal to state 1. And then what you can do is the same deal. Since it's very repetitive behavior, I can do a lot of copying and pasting here, and then just change from state 1, we go to state 2, state 2, go to state 3, state 3, we go to state 0, right? I believe that is the behavior. So if we simulate this, my test bench, still good, right? So we can pull in all of our signals here. And like I was saying earlier, if you actually go over here to the sim tab, Questa, dot is the name that we named our instance in our test bench, since we're simulating our test bench. If we click on that real quick, you can see state R pulls up because the signal actually appears whenever we're referencing our dot. And basically we want to pull in that internal signal for the state register to see what's going on. Bang, that, end of loop. Oh, awful. So let's zoom in a little bit. And this is our output binary. So obviously we don't have a default. What we can do here is we can just say when it's reset, we can set output equal to just zeros. That's not necessarily what we want, but let's see what happens here. One moment. What's happening? What? Oh, it's still going, bruh. So state 0, right? It starts here, but then reset is low, right? So when reset gets pulled low, right, we enter here, we see our state is state 0. Our output then becomes this, and since this is synthesizing to essentially like a register as well, basically we can see on the next cycle after this first clock edge when clock is rising edge and reset is 0. We see that, yeah, an enable is still not 1 yet. So it'll stay here and it doesn't transition. It stays here, and on this next edge, it's still obviously the state will transition, but the output won't change yet. So as we can see here on this next edge over here, so I guess we'll go edge by edge. So here first, we can see enable is true. And basically on this next edge here, the state will change. And then in this next state, we define the output to be this. So then on the next clock after that, our output will change, right? And so on and so forth. Since enable is updated, basically state 0, this is the value that should be in state. And then basically it's like that. So as you can see, it updates like that. And that's the functionality of the more. But then what we can do here is we change this to the transition and update it on the transition. We can see some difference in the behavior. Oops. So let's take a look at what's going on there now. So if we do that, hello? My goodness, don't know what that's about. Yeah, here we go. So we can see enables true, state transitions. And that's only being like that because I need to just set that default value back to that actually. But yeah, so state 0, and then when it gets to state 1, the value of output is that when it gets to state 1. So we could see the difference of assigning it on the transition rather than in the state, if that makes sense. And it just keeps looping. And yeah, that is the difference of Mealy and Moore. And this has different implications depending on your application or whatever you're trying to do. But that is essentially the workshop. And I know that was probably pretty long, and I know I may have rambled a little bit, but I appreciate everyone being still good, still intact, being watching and trying to learn what you can from this. But again, thank you. I think we're gonna wrap it up now. If you have any questions, message anyone in the Discord. Plug out PG Gators. I was Yoni, and we still good. All right. Bye bye. Yeah, everyone that's here will stand for questions. All right, see.